The Great Pyramid of Giza defies simple explanation even today. This video uncovers 25 forgotten engineering methods that built the impossible monuments of antiquity. You will gain a completely new lens for seeing history, one that reveals a lost world of intellect and innovation. How did cultures without modern machinery move 100-ton stones or create concrete that strengthens underwater for 2,000 years? We will journey from the interlocking walls of the Andes to the volcanic ash formulas of Rome, piecing together a hidden blueprint of human achievement. What do you believe is the greatest legacy of these ancient builders? The first method begins with something delicate, something temporary. A sculptor in a world without steel tools carves a form from beeswax, perhaps a roaring lion or an ornate ceremonial vessel. This soft, pliable model is the heart of a technique known as lost wax casting. The artist then encases this fragile wax original in a thick layer of clay, creating a ceramic shell. The crucial moment comes when this sealed mold is heated in a fire. The wax melts completely, draining out through a small channel, leaving behind a perfect hollow cavity within the hardened clay. Into this empty space, molten bronze or glowing gold is poured, filling every minute detail the wax once held. Once the metal cools and the clay shell is broken away, a perfect metal replica of that original wax model is revealed. This was not a secret held by one culture, but a shared innovation spanning from the workshops of Mesopotamia to the skilled metalworkers of the Indus Valley. It allowed for the creation of objects of stunning complexity, like the lifelike statues that defined classical Greece or the intricate golden artifacts of the Moche people in South America. This process was, in essence, an ancient form of mass production, enabling the precise replication of intricate designs without a single modern machine. So why did such a brilliant and widespread method eventually fade from prominence? Its decline was likely a slow dance of changing trade routes and the availability of materials, a quiet shift that would eventually make way for the next great leap in metalworking, a story of fire and iron that we will soon uncover. While the lost wax process mastered metal, another forgotten art was shaping the very bones of the earth. In the high Andes of Peru, the fortress of Sacsayhuamán presents a stone puzzle that defies belief. Enormous blocks, some weighing hundreds of tons, are locked together in a colossal jigsaw. Their edges are neither straight nor uniform, but a complex tapestry of convex and concave curves, fitting so flawlessly that even a razor blade cannot find a purchase. This is polygonal masonry, a method that traded the simplicity of rectangular blocks for the profound strength of interlocking forms. Without a single drop of mortar, these walls became a single, unified entity. The secret was not in forcing the stone to conform to a blueprint, but in allowing each unique block to find its perfect neighbor. Researchers like Jean-Pierre Protzen have suggested builders likely used a process of iterative fitting. They would shape a stone roughly, place it against its neighbor, and identify the high points. Then, through patient abrasion with harder stones, they would grind away these points over and over until the two faces merged into one continuous surface. This was not quick construction, but it was construction for the ages. The resulting wall was incredibly resilient. When the ground shook during an earthquake, the interlocked stones would shift and settle, dissipating the energy throughout the entire structure rather than cracking apart. This same principle can be seen in the deep foundations of Roman temples and the massive stone bases of Japanese castles, a global testament to its brilliance. How did these builders visualize such intricate, three-dimensional puzzles without detailed plans? It speaks to a deep, intuitive understanding of geometry and stress, learned through generations of patient observation and refined through countless acts of trial and error. But this mastery over solid rock leads to a different, almost paradoxical question. What if the most enduring material of the ancient world was not stone at all, but a liquid that chose to become one? The liquid that chose to become stone was Roman concrete. While the massive blocks of the Andes stood firm on land, Roman engineers faced a different challenge: the relentless sea. At the harbor of Caesarea, great breakwaters were submerged, yet 2,000 years later, these concrete masses remain stronger now than the day they were poured. Their secret was not just a recipe, but a magical ingredient, a volcanic ash known as pozzolana. When this fine, dark sand from places like Pozzuoli was mixed with lime and chunks of rubble, it created a chemical marvel, a hydraulic concrete that could not only set underwater but actually gain strength from it. Modern materials scientists like Marie Jackson have dedicated their careers to unraveling this ancient alchemy. They discovered that seawater reacting with the pozzolana mixture triggers the slow growth of rare, interlocking crystals. These minerals weave through the concrete, blocking cracks and reinforcing the structure from within, turning a man-made mixture into something that behaves more like a living rock. This was the material that allowed the Romans to build the soaring, unsupported dome of the Pantheon and the aqueducts that quenched the thirst of 1 million people. It was the foundation of their maritime empire, enabling ports across the Mediterranean to thrive with infrastructure that modern concrete, which can crumble in decades, struggles to match. The Romans looked at a volatile landscape of volcanoes and saw not just destruction, but a building material for the ages. This brilliant use of a natural resource makes you wonder, what other earth materials did ancient cultures learn to awaken? Granite is one of the hardest stones on Earth, yet along the banks of the Nile, ancient artisans sliced into it as if it were soft wood. The evidence is not just in the finished monuments, but in the discarded clues they left behind, like the famous granite core sample discovered at Giza. This stone cylinder, now in a museum, is marked with a deep, consistent spiral groove, a perfect record of a tool that bit relentlessly into the heart of the rock. This was the work of the tube drill. Workers used hollow copper tubes, likely weighted and turned by a bow-like mechanism, but the real magic was in the abrasive. They employed a simple, brilliant partner, ordinary quartz sand. Poured into the cutting area, these hard, sharp grains became millions of microscopic cutting teeth, allowing the relatively soft copper to grind its way through even the toughest diorite and basalt. The precision this method achieved is staggering. Look at the sarcophagi inside the Great Pyramid, their interiors hollowed out with corners so sharp and surfaces so smooth, they suggest a technology we struggle to explain even with our modern knowledge. Engineer Christopher Dunn has studied these tool marks extensively, noting the uniform feed rate the grooves imply, a sign of sustained, powerful, and controlled force. This was not a haphazard process. It was a systematic application of physics, where human ingenuity amplified simple materials to achieve the impossible. The unfinished obelisk in Aswan offers a frozen moment in this process, with drill holes marking the path where workers intended to separate the colossal stone from the bedrock, their tool marks still visible as clear channels. This quiet mastery over solid rock forces a profound question. How many other ancient methods remain hidden in plain sight, not because the evidence is lost, but because we have not yet learned to see the world through the eyes of the builders themselves? The mastery of stone in the Andes extended far beyond fortress walls to the very pathways that connected a vast empire. High in the mountains, the Inca road system, the Cuhapac Ñan, clings to slopes so sheer it seems to defy gravity itself. Its endurance over centuries lies in a forgotten art of road construction that understood the land as a living partner, not an obstacle to be conquered. The Incas did not simply cut trails. They sculpted the terrain with interlocking stone retaining walls that transformed unstable slopes into stable, graded terraces. These walls did more than just hold back the earth. They created a foundation that could breathe and shift with the mountain. But perhaps their most brilliant innovation was invisible until the rains came. Integrated directly into the roadbed were carefully designed drainage channels and culverts. These features worked in harmony to capture torrential rainwater and guide it safely away, preventing the erosion that would have washed a lesser road down the mountainside in a single season. Researchers like John Hislop have documented how this network, spanning thousands of miles, was built with profound local knowledge. Workers used materials at hand, fitting stones without mortar and layering gravel for stability, principles that modern civil engineering still employs. This was infrastructure built not for speed, but for eternity, facilitating communication and control across an empire of incredible diversity. The roads bound the Inca world together, a testament to a culture that looked at a raging river on a cliffside and saw not a barrier, but a puzzle to be solved with patience and stone. How did ancient engineers confront the ultimate barrier? Not a mountain to be traversed, but the solid earth itself that needed to be pierced from within. The ambition of classical architecture literally rose on the backs of men walking in circles. High above the construction site of the Parthenon, a massive wooden wheel turned steadily, not by a beast of burden, but by the relentless steps of laborers pacing inside its frame. This was the Treadmill Crane, a machine that transformed human strength into monumental force. Roman engineer Vitruvius detailed its workings, describing a system of rope, pulleys, and a central drum. The genius was in its mechanical advantage. By walking the wheel, a small team could generate enough power to hoist multi-ton marble blocks with a slow, controlled precision that brute force could never achieve. This was not about mere lifting. It was about placing stone upon stone with the exactitude demanded by Greek temples and later, the soaring arches of the Colosseum. The repetitive, predictable motion meant workers could operate for longer periods without the intense strain of direct hauling. Some of these wooden giants were even designed to be taken apart and reassembled, moving from one grand project to the next across the empire. Carvings on Roman tombs and illustrations in medieval manuscripts show the treadwheel's evolution into more complex forms, proving its lasting legacy. With such power at their fingertips, architects were no longer bound by the limits of the ground. They could dream in vertical lines, stacking the sky with columns and vaults. But a crucial question remained once these massive stones were lifted into place at the quarry. How did builders move them across miles of rugged land to the building site itself? A multi-ton obelisk begins to glide across the desert, not on wheels but on a path of its own making. This was the reality of megalithic transport, a slow dance of wood, water, and human coordination. Teams of workers moved colossal stones on a bed of wooden rollers, constantly repositioning the logs from the back to the front as the massive block inched forward. The true innovation, however, was underfoot. Tomb paintings and experimental archaeology by researchers like Mark Lehner suggest they used water or slick mud to lubricate the prepared pathway, dramatically reducing friction. This simple liquid layer transformed an impossible task into a manageable one, allowing a coordinated team to pull stones weighing hundreds of tons. We see this principle echoed across the globe, from the famous Moai statues of Easter Island, which may have been walked upright in a rocking motion, to the gargantuan columns of Baalbek in Lebanon. The process was a testament to logistics and rhythm, not brute force. It required a deep understanding of physics and meticulous planning to maintain a level path and ensure the stone did not settle or shift dangerously. But once these monumental stones arrived at their destination, a new and even more precise challenge emerged. How did ancient builders ensure that a towering wall was perfectly vertical, or that a vast temple complex was aligned with the stars? This demanded a different kind of tool, one that could translate grand visions into exact lines on the ground. a Roman engineer stands on a patch of uneven ground, a simple wooden cross in his hands. This was the Groma, an instrument of profound simplicity that could draw a perfectly straight line across miles of rolling hills. At the end of each of its 4 arms hung a plumb bob, a weighted string. By sighting across 2 opposing pairs of these vertical lines, the engineer could establish a flawless right angle or extend a single, unwavering path into the distance. This was the tool that laid out the relentless straightness of Roman roads and the grand grid plans of new cities, imposing geometric order upon the natural chaos of the landscape. Yet for all its power, the Groma could not solve the problem of leveling. For that, Roman builders turned to an even more elegant solution, the water level. Imagine a long hose or a trough filled with water. No matter how the terrain rises or falls, the surface of that water at both ends will always find the exact same horizontal plane. This principle of communicating vessels gave them a constant, unerring reference line. Experts like Trevor Hodge have detailed how these tools, in combination, were the backbone of Roman infrastructure. An aqueduct channel had to maintain a precise, gentle slope for miles, a feat impossible without the water level to guide its construction. This ensured that water flowed steadily from the mountains to the cities, a lifeline of engineering that functioned for centuries. These were not complex machines, but profound applications of basic geometry and physics, mastered through observation. But how did these principles of line and level translate into the soaring, curved forms of arches and domes that defined their most majestic structures? The straight line had to learn to bend. The towering lion gate of Mycenae presents a puzzle of immense weight and perfect balance. Its famous triangular opening is not a true arch, but a masterpiece of the Corbelled Vault, an ancient method of stacking stones in ever-overlapping layers until they meet at the peak. This technique, used with stunning effect by the Mycenaeans in structures like the Treasury of Atreus, and independently perfected by the Maya at sites like Palenque, was a brilliant early answer to a fundamental challenge: how to roof a space without a forest of supporting columns. Each stone block was precisely cut so that it projected slightly inward over the one below it, gradually closing the gap overhead. The entire weight of the structure was channeled outward and downward, transferred into massively thick supporting walls that acted as a counterbalance. Archaeologists such as George E. Milonas have detailed how this method avoided the need for complex wooden frameworks or centering that true arches require. It was a patient, incremental approach to creating grandeur, one that produced the soaring, narrow chambers of Maya palaces and the awe-inspiring, beehive-shaped tombs of Mycenaean kings. Yet for all its strength, the corbelled arch had a limitation. Its outward thrust demanded those heavy, bulky walls. The next great leap in architectural history would find a way to turn that thrust into a source of strength itself, creating a structure that could carry its own weight with elegant efficiency. This was the birth of the true arch, a revolution in stone that would change the world. The true arch represents a fundamental shift in how humanity understood weight and support. Unlike the stacked stones of a corbelled vault, the true arch is a single, cohesive structure born from a perfect arrangement of wedge-shaped blocks known as voussoirs. Each stone leans against its neighbor, and the central keystone at the very top locks them all into place. The immense load from above is not just pushed downward, it is cleverly transformed, channeled sideways along the curve of the arch, and directed into the sturdy pillars or abutments on either side. This elegant distribution of force is what allowed Roman engineers to span vast distances with breathtaking openness, creating the airy arcades of aqueducts and the grand entrances of amphitheaters. While the Romans did not invent the concept, they perfected it with an almost obsessive precision. Scholars like John B. Ward Perkins have documented how they standardized the shapes and sizes of the voussoirs, turning arch construction from a specialized craft into a repeatable, rapid process. They combined this stonework with their miraculous concrete, creating structures that were not only strong but also resilient and surprisingly quick to build. The result can be seen in masterpieces like the Pont du Gard in France, a three-tiered aqueduct that has carried the weight of centuries as effortlessly as it once carried water, and the triumphant Arch of Constantine, where the arch itself became a symbol of power and permanence. This revolutionary form did more than just create stronger buildings. It fundamentally changed the space within them, offering vast, uninterrupted interiors. But this very success pushed the ambition of builders to its logical extreme. If a single arch could span a wide space, what could a continuous series of arches, rotated around a central point, achieve? The answer was a structure that seemed to capture the very heavens, the dome. The dome of the Pantheon in Rome does not simply rest upon its walls, it floats above them. To achieve this illusion of weightlessness, Roman engineers employed a masterful deception, building the massive structure with progressively lighter materials as it ascended. At its thick, concrete-heavy base, the mixture was dense with heavy travertine and brick, but layer by layer the aggregate changed, shifting to lighter stones like tufa and finally to porous pumice at the very top. This gradual lightening minimized the overall load, but the true genius lay hidden within the curve itself. Encircling the dome's interior are 5 massive step rings, which architect David Moore analyzed as integral compression rings. These rings act like a tightened belt, absorbing the dome's natural tendency to push outward and channeling that force safely back into the structure. The famous oculus at the summit is not merely a dramatic source of light, it is a calculated engineering decision. By leaving the center open, the builders eliminated the heaviest, most unstable part of the dome, the keystone, turning a potential weakness into a source of both illumination and stability. This single structure created an interior space of breathtaking scale, a room that felt as vast as the sky itself, and its principles would echo through the ages in the great baths, temples, and cathedrals that followed. But this mastery of stone and concrete represents only one branch of ancient roofing genius. What happened in lands where stone was scarce or the forests were plentiful? This question draws our attention upward to the intricate skeletons of wood that sheltered entire civilizations under vast protective canopies. High above the Forbidden City, the great halls stand without a single nail holding their skeletons together. This was the art of Mortise and Tenon joinery, a form of three-dimensional woodworking so advanced it turned timber frames into resilient, breathing entities. A tenon is a precisely carved projection on the end of one beam, while a mortise is the perfectly fitted socket carved into another. When joined, they form a connection that is both incredibly strong and surprisingly flexible. This principle was codified in ancient Chinese technical manuals like the Yingzhou Fashi, which detailed thousands of joint variations for every conceivable structural need. The result was architecture designed for permanence through adaptation. In a powerful earthquake, a rigid iron-nailed structure might shatter, but a mortise and tenon frame would sway and shudder, its joints flexing to absorb the violent energy before settling back into place. Scholars like Nancy Schatzman-Steinhardt highlight how this system allowed for entire buildings to be disassembled, repaired, and even relocated, a testament to a circular, sustainable mindset centuries ahead of its time. The towering pagodas of Japan, which have weathered countless typhoons and tremors for over 1,000 years, are living proof of its effectiveness. The wood itself was understood as a partner, its grain, its strength, and its natural movement all respected and harnessed within the joinery. This deep material wisdom raises a fascinating parallel. If wood could be woven into a frame that supported immense weight, could the same principle be applied to the very walls of a home, using the humblest of materials? While wooden frames created the skeletons of great halls, The walls themselves were often filled with a humble yet brilliant composite of earth and fiber. Across Europe and beyond, builders wove flexible willow or hazel branches into a tight lattice known as wattle. This woven grid was then packed on both sides with daub, a sticky mixture of clay, animal hair, and straw, sometimes strengthened with other local materials. The result was a surprisingly resilient wall panel, lightweight yet possessing excellent thermal mass. It kept interiors cool in summer, and when combined with a central hearth, warm in winter. Experimental archaeology at places like Butzer Ancient Farm has demonstrated the true durability of this method. Researchers, following the work of archaeologists like Peter Reynolds, have shown that a well-maintained wattle and daub wall could protect a home for generations. This was not a primitive stopgap, but a sophisticated understanding of material science. The combination created a wall that could breathe, allowing moisture to pass through without rotting the structure, and that had enough flex to withstand the settling of a timber frame without cracking. Its low cost and speed of construction made it the standard infill for everything from peasant cottages to the walls of early medieval forts. But this very adaptability points to its limitation, a reliance on a sturdy frame and a need for regular upkeep against the elements. So, for structures demanding greater permanence and bearing their own weight, what material could offer the strength of stone with the simplicity of earth? The answer was waiting in the mud and the heat of the sun. The sun-baked earth itself became a building block in the hands of ancient innovators. From the banks of the Nile to the arid landscapes of the American Southwest, communities perfected the art of Adobe brick production, a method that transformed humble soil into architecture of remarkable endurance. This was not merely drying mud in the sun, it was a sophisticated science of material selection. Builders sought out specific clay-rich soils and mixed them with a crucial ingredient, chopped straw or other organic fibers. Anthropologists like E.B. Sales documented how this binder acted like a natural reinforcement, a web of tiny threads that prevented the bricks from cracking as they shrank during the curing process. These mixtures were packed into wooden molds and then laid out for the most crucial craftsman of all, the sun itself. Solar curing over days or weeks slowly drew out the moisture, leaving behind a solid, stable brick. The construction continued this theme of mass and stability. These bricks were stacked with mud mortar to create incredibly thick walls, sometimes several feet deep. These walls acted as a natural thermal battery, soaking up the day's heat and slowly releasing it during the cool desert nights, creating comfortable living spaces without any mechanical aid. The citadel of Bam in Iran and the multi-storied structures of Taos Pueblo stand as breathtaking testaments to this method's resilience. Their organic, rounded forms have survived centuries of earthquakes and extreme weather precisely because of their flexibility and immense mass, which allows them to absorb and dissipate energy that would shatter a more rigid structure. This was perhaps one of the most sustainable building techniques ever developed, using only local earth and solar energy, leaving a minimal footprint on the land. But a fundamental question arose from this sun-powered process. How could these communities create earthen bricks that could withstand the relentless erosion of heavy rains? The search for greater durability in wetter climates would eventually lead builders from the open air of the sun to the contained, transformative heat of the kiln, unlocking the next evolution of the brick. The gleaming Fa-A-tilde section Adeva ziggurat was a testament to a revolution in fire. In Mesopotamia, around 3,000 years before the Common Era, builders moved beyond the sun's gentle drying to the fierce, controlled heat of the kiln, transforming ordinary clay into a new material, the fired brick. This was a leap in durability that allowed architecture to defy the elements. Sun-dried adobe could melt away in a heavy downpour, but a properly fired brick underwent a chemical change called vitrification. The silica in the clay fused together, creating a hard, waterproof ceramic shell that could last for millennia. scholars like Seton Lloyd have detailed how this required constructing specialized kilns, chambers that could consistently reach temperatures high enough to trigger this alchemical transformation. The impact was profound. Firing allowed for the standardization of brick sizes and shapes, which in turn revolutionized the speed and scale of construction. Workers could now rely on uniform blocks, making complex projects like arched doorways and intricate, decorated facades far more efficient to build. The most stunning example is the Ishtar Gate of Babylon, a structure that showcased how firing unlocked both structural and artistic genius. Its bricks were not only durable, they were coated in vibrant, glazed colors, creating a shimmering vision of dragons and bulls against a lapis lazuli blue background. This single innovation turned a humble, earthen material into a medium for monumental and enduring art. The mastery of clay and fire in the kiln naturally raises a broader question. If they could create such resilient building blocks, what other wonders were they shaping from the very same earth? This exploration leads us from the grand scale of city gates to the intricate, life-sized creations of an emperor's subterranean army. Baked clay became more than just a brick. It became a skin of armor and art for ancient structures. Across the Mediterranean, Greek and Etruscan temples were often clad in vibrant terracotta panels, sheets of fired clay that shielded vulnerable wooden rafters and mud brick walls from the relentless rain. These were not merely functional covers, they were canvases for expression. Artisans pressed wet clay into molds to create intricate reliefs depicting myths and deities, or shaped it into decorative roof tiles and statues known as antefixes, which lined the eaves of buildings. Scholars such as John Boardman highlight how this technique allowed for elaborate, repeating patterns that would have been prohibitively expensive and time-consuming to carve directly from stone. The clay was then fired, transforming it into a lightweight, durable, and waterproof ceramic shell that could be easily attached. This principle of mass-producing beautiful, protective elements reached a breathtaking scale with the terracotta army of Zion, where thousands of life-sized figures, each with unique features, were created from a modular system of fired clay parts. This approach made architectural grandeur more accessible, allowing smaller cities to adorn their public buildings with a splendor that echoed the great capitals. But adorning a structure was one thing, ensuring its very bones could withstand immense weight and time was another. This challenge led builders to a hidden innovation, one that involved weaving a skeleton of metal into the heart of their stone and brick. The marble blocks of the Parthenon were locked together with a hidden skeleton of iron. In a world before steel beams, Greek and Roman engineers embedded metal clamps and dowels deep within the stone itself to create structures of impossible slenderness and height. These were not simple bars, but carefully forged pieces shaped like double T's or swallowtails, designed to fit into perfectly carved grooves on the faces of adjoining blocks. Once the clamp was seated, the final touch was an act of ancient alchemy, pouring molten lead over the iron to seal it completely from the air. This lead jacket was a brilliant innovation, a protective measure against the rust that could otherwise spell the structure's doom. As described by engineers like J. Colton, this system transformed the way loads were carried. Stone is incredibly strong under compression, but brittle and weak when pulled apart. These metal fittings gave the masonry a new kind of strength, tensile strength, allowing it to resist the lateral forces of wind and earthquake that would make a simple stack of stones tumble. We can see this same principle at work in the grand ruins of the temples at Selinunt in Sicily and in the soaring walls of the Roman theatre in Orange, France. The metal acted as an internal ligament system, binding the skeleton of the building into a cohesive, resilient whole. Yet this reliance on imported metal posed a challenge for cultures without easy access to iron or lead. How did builders in remote areas or with fewer resources achieve a similar, lasting bond between their stones? Their solution was not forged in a furnace, but mixed in a pit, turning the most common materials on Earth into a glue that could last for millennia. The heat of a medieval kiln transformed ordinary limestone into a substance of almost magical power. Masons carefully burned the stone in a process called calcination, driving out carbon dioxide and leaving behind a highly reactive material known as quicklime. The true moment of transformation, however, came with the slaking. When water was added to this quicklime, it triggered a violent steaming reaction, releasing intense heat as the powder swelled and softened into a smooth, pliable paste called lime putty. This putty was the heart of a mortar that could bind stones for 1,000 years. Unlike modern Portland cement, which forms a rigid, brittle bond, lime mortar hardens through a slow, gentle process. It reabsorbs carbon dioxide from the air over decades, gradually turning back into a form of limestone, creating a joint that is both strong and flexible. Engineering historians like Robert Mark have detailed how this flexibility was its greatest strength. As a stone wall settles or shifts with the seasons, the lime mortar gives just enough to accommodate the movement, preventing the stones themselves from cracking. This is why the magnificent Gothic cathedrals of Europe, with their soaring heights, and the serene, domed stupas of South Asia have endured for so many centuries. The mortar joints could be carefully repointed and repaired, allowing the structures to be maintained generation after generation. But what happened when these builders needed to construct in a harbor or a damp foundation where the slow-setting air lime would simply wash away? Their ingenious solution was to return to the wisdom of their Roman predecessors, blending the lime with specific additives to awaken a hidden property, creating a mortar that could set even underwater. A thick, black substance bubbled over a fire near the banks of the Indus River. This was bitumen, a naturally occurring asphalt that ancient engineers transformed into one of the world's first and most effective waterproofing agents. As early as 4,000 years before the Common Era, the builders of Mohenjo-Daro were carefully heating this material until it liquefied, then brushing it onto the interiors of brick drains and great bath structures to create a seamless, impermeable seal. This same sticky, resilient substance was gathered from natural seeps across Mesopotamia, where it was used to coat the hulls of trading boats and to line vast reservoirs, ensuring precious water did not seep back into the thirsty earth. Scholars like Zainab Baroni have documented how this material was more than just a simple sealant. It represented a profound early grasp of practical chemistry. Its application was remarkably diverse, from cementing the joints of ziggurates against the rain to its use in ceremonial practices far from the world of construction. The docks at Lothal, part of the same Indus Valley civilization, showcase this engineering perfectly, with bitumen-lined locks that managed tidal water flow for a bustling port. Its decline was slow, a gradual shift as other sealants like lime mortar became more accessible, but for millennia, this black gold from the earth was the key to creating structures that could defy water itself. This mastery of organic materials makes you wonder, what other pliable, natural substances did these builders weave into their grand designs? The answer lies not in stone or tar, but in the very fibers that could be spun into threads of incredible strength. Fibers from the dry Andean grass known as iku were woven by hand into the very mud of an adobe brick, creating a composite material of unexpected strength. This was not a rare secret, but a global principle of vernacular engineering. From the straw-laced plaster of Egyptian tombs to the animal hair mixed into European daub, ancient builders understood that adding a flexible skeleton to earthen materials transformed their behavior. The stiff grass stems or straw fibers acted as a natural mesh, a microscopic web of reinforcement that held the clay particles apart. This prevented the mud from shrinking and cracking apart as it dried, but its true genius was revealed under stress. When the ground shook, these fibers allowed the wall to flex and absorb the energy rather than shattering like a solid, brittle block. Researchers like Kenneth R. Wright have documented how this very principle gave resilience to the vast adobe city of Chan in Peru, where immense, ornate walls have withstood centuries of seismic activity. The fibers distributed the forces throughout the material, creating a toughness that pure earth could never achieve on its own. This was an intuitive grasp of tensile strength, solving a fundamental weakness of masonry long before the invention of modern rebar. But how did cultures apply this knowledge on a truly monumental scale, moving beyond bricks to reshape entire landscapes? The answer lies not in the material itself, but in the earthen pathways built to carry it skyward. The final stones of the Great Pyramid were hauled into place on a mountain of earth that no longer exists. This was the logic of the construction ramp, a temporary landscape of compacted rubble and clay that rose with the pyramid itself, only to be dismantled and swept away upon the project's completion. Egyptologist Mark Lehner's research at Giza has uncovered tantalizing traces of these massive inclines, providing physical evidence for a method long theorized from tomb paintings and texts. These were not simple piles of dirt, but carefully engineered structures. Builders likely constructed them in either a long, straight ascent or a spiraling path that wrapped around the pyramid's rising faces, each design offering a trade-off between the volume of material needed and the logistical challenge of navigating corners. The slope had to be precise, steep enough to be manageable in length, yet gentle enough for teams of laborers to drag multi-ton stone blocks on wooden sledges. The edges of these ramps were often reinforced with timber or brick retaining walls to prevent catastrophic collapse under the immense, shifting loads. The sheer amount of work involved in building and then removing these colossal earthworks is almost as staggering as the pyramid they helped create. It was an act of monumental effort designed to erase its own footprints, leaving behind only the pristine geometric form. Experimental archaeology has powerfully demonstrated the feasibility of this approach. When combined with the simple trick of wetting the sand or mud in front of a sledge to drastically reduce friction, the seemingly impossible task of lifting stones hundreds of feet into the air becomes a slow, rhythmic, and achievable process of human coordination. This grand solution to vertical transport, however, was not the only tool in their arsenal. For the final, most delicate placements at the very summit, how did they achieve the precision that brute force dragging could not provide? This challenge would have demanded a more elegant and intimate application of physics, moving from the collective power of the ramp to the focused ingenuity of the lever and counterweight. A single misstep could shatter a 100-ton obelisk into worthless fragments. To prevent this, ancient engineers turned a simple playground principle into a method of monumental precision: the lever and counterweight. Imagine a massive stone needle lying beside its pedestal, with one end resting on a fulcrum of timber. Teams would methodically fill enormous containers with dry sand, hanging them from the elevated end of the obelisk. Each bag acted as a precise, adjustable weight. By slowly releasing sand from these containers, they decreased the counterweight in tiny, controlled increments. This allowed the obelisk to rise from the ground with a gentle, inexorable grace, a fraction of an inch at a time. It was physics in its purest form, a perfect balance between the stone's immense mass and the escaping grains of sand. Engineers like Reginald Engelbach have studied this process, noting how it transformed an act of brute force into one of delicate control, dramatically reducing the risk of a sudden, catastrophic slip. The great obelisks at Karnak and the Lateran obelisk in Rome likely rose into the sky through such a patient, rhythmic dance. Temporary wooden frameworks surrounded the operation, bracing the stone as it ascended to ensure it never swung or tilted unpredictably. But this careful ballet of leverage only solved the problem of getting the stone upright. A new and equally critical challenge began the moment the obelisk stood vertical. How did they ensure this towering monolith, now swaying precariously on its narrow base, would remain standing for millennia against wind and tremor? The answer lies not in the sky, but deep within the earth, in a foundation designed to become one with the stone it supported. The stability of a monument begins long before the first stone is laid, in the hidden world beneath our feet. Ancient builders understood that a structure's true strength was determined by its foundation, and they developed sophisticated methods to conquer unstable ground. At Stonehenge, the massive sarsen stones were not simply dropped into holes. Archaeologists like Mike Parker Pearson have revealed how workers excavated deep trenches, then carefully layered the bases with packed gravel. This acted as a primitive but highly effective drainage system, channeling rainwater away from the stone's base to prevent the waterlogged soil from softening and causing the monoliths to shift or sink over centuries. This was more than just a stable platform. It was a deliberate intervention in the landscape to ensure permanence. For even greater challenges, such as the soft, marshy ground where Rome built its bridges or where entire cities like Venice would one day rise, engineers turned to pilings. They drove long, sharpened logs of oak or pine deep into the waterlogged sediments, often until these wooden posts hit a more solid, load-bearing layer of earth far below. A cluster of these pilings, packed tightly together, created an artificial island of stability in the soft ground. The weight of a bridge pier or a building wall was then distributed across this entire network, preventing a catastrophic settlement. This was a fundamental principle of geotechnical engineering, applied millennia before the science had a name. It was a dialogue with the earth itself, testing its limits and reinforcing its weaknesses. But placing a stone on a stable base was only half the battle. How did they ensure that an entire circle of stones, or a temple stretching for hundreds of feet, was oriented with such breathtaking precision to the sun or the stars? This final alignment demanded a different kind of foundation, one laid out not in the soil, but across the heavens themselves. The rising sun on the shortest day of the year did not merely illuminate the tomb at Newgrange, it entered it. A narrow beam of light pierced through a specially designed roof box above the entrance, traveling down a long, dark passage to flood the inner chamber with golden light for precisely 17 minutes. This was not an accident of architecture, but a deliberate act of alignment, a frozen moment of celestial engineering repeated annually for over 5,000 years. This profound connection to the heavens is our 24th forgotten method, a discipline where the sky itself was the ultimate blueprint. From the pyramids of Giza, aligned with near-perfect cardinal orientation, to the Mayan observatory of El Caracol, whose strange windows precisely track the complex cycles of Venus, ancient builders embedded cosmic knowledge into stone. Researchers like Anthony Aveni, a founder of archaeoastronomy, have shown this was a global phenomenon. The Incas at Machu Picchu positioned the Intihuatana stone, the hitching post of the sun, to cast specific shadows during the equinoxes, marking the agricultural calendar with stone and shadow. These alignments served a deep, integrated purpose, blending spiritual belief with practical necessity, ensuring rituals were performed at the correct celestial moment and that communities knew precisely when to plant and harvest. Achieving this required generations of patient observation, a meticulous recording of the sky's movements, and a sophisticated understanding of geometry to translate those celestial paths into terrestrial lines. But such grand visions, etched in the stars, could not be left to chance on the ground. How did an architect convey the precise angle of a solstice alignment or the exact proportions of a towering pyramid to the thousands of workers who would build it? This final challenge demanded the first universal language of engineering, a miniature vision of the magnificent whole. A miniature clay tablet, barely larger than a hand, held the complete blueprint for a temple that would tower over a city. This was the final forgotten method, the ancient art of scaled planning, where grand visions were first captured in miniature on clay and papyrus long before a single stone was laid. Babylonian architects, as evidenced by statues of the ruler Gudea showing him with a building plan on his lap, used styluses to incise precise diagrams onto wet clay tablets. These were not rough sketches, but carefully proportioned technical drawings, often using a consistent scale to relate the small diagram to the immense final structure. In Egypt, the Turin papyrus map reveals a stunningly accurate, scaled plan of a gold mine and its surrounding geology, a tool for resource management as practical as any modern blueprint. Scholars like John A.R. Legon have decoded how Egyptian architects used a grid system based on the royal cubit, a standardized unit of measurement. This grid allowed them to translate the perfect proportions of a statue or the complex layout of a tomb directly from a small papyrus sheet to the full-scale construction site with remarkable consistency. This practice was a powerful form of early project management. It allowed a master architect to communicate his exact intent to hundreds of workers, ensuring that teams carving in distant quarries and masons building on site were all working in harmony toward the same unified vision. These scaled models and plans enabled patrons and clients to visualize and approve a design before committing vast resources of labor and material, preventing costly errors and streamlining the entire construction process. So what overarching principle tied this method to the 24 that came before it, from lost wax casting to celestial alignment? The common thread is a profound dialogue with the natural world. These builders were not conquerors of their environment, but astute observers and collaborators. They learned to amplify the strength of stone through interlocking shapes, to awaken the hidden potential of volcanic ash and lime, and to harness the very forces of gravity and leverage that govern their universe. Their legacy is not a list of isolated tricks, but a holistic philosophy of engineering, one that blended deep material wisdom with celestial mathematics and meticulous planning. It was a wisdom built on patience, on generations of accumulated knowledge, and on a humble respect for the materials and laws of the world they sought to build upon. These 25 forgotten methods are not a random list of tricks, but a single, unified philosophy of engineering. The common thread woven through lost wax casting, polygonal walls, and self-healing concrete is a profound dialogue with the natural world. Ancient engineers were master observers. They watched how stones settled on a hillside, how mud cracked in the sun, and how certain sands would harden in water. They did not have formal textbooks on physics or chemistry, yet they learned to leverage gravity, friction, and chemical reactions with an intuitive genius. They saw the potential in the materials immediately around them, transforming volcanic ash into eternal harbors and weaving common grass into earthquake-resistant walls. This was innovation born of deep adaptation, not brute force. The Romans did not fight the sea, they invited it to strengthen their concrete. The Incas did not conquer the mountain, they collaborated with its slopes to build roads that breathed with the land. Every technique reveals a core principle of sustainability and longevity, a patience that stands in stark contrast to the haste of much modern construction. Their legacy is a heritage of brilliant problem-solving that perfectly balanced ambition with resourcefulness. So what can we truly learn from this lost blueprint? The question is not just one for historians, but for every engineer, architect, and builder today. How can we rediscover that art of working with nature rather than against it, to create structures that are not only impressive but enduring and wise? The silent stones of ancient monuments are not puzzles waiting to be solved, but stories waiting to be heard. Our journey through 25 forgotten methods reveals a simple, profound truth. These structures are not miracles, but monuments to human ingenuity and relentless perseverance. They stand as the culmination of knowledge carefully passed from one generation to the next, refined through countless acts of trial and error, and then applied on a breathtaking scale. The real magic lies not in lost technology, but in a lost way of thinking. It was an approach that saw potential in the most common materials, harnessing the very forces of nature like gravity and water as partners in creation. True innovation, it seems, does not always demand the newest tools. Sometimes it asks only for a deeper observation of the world already in our hands, from the volcanic ash at our feet to the predictable paths of the stars overhead. Let this exploration change how you see the ancient wonders that still grace our world. Look closer at the interlocking stones of an old wall or the graceful curve of a Roman aqueduct, and see them for what they are, a hidden blueprint of human achievement. Perhaps their greatest lesson is one we can carry forward, a reminder to build with patience, to design with the land, and to create with a vision for the millennia to come. If this journey into history's hidden workshop has inspired you, we would be grateful if you shared your thoughts. Which of these ancient methods left you in the greatest awe? Let the conversation continue in the comments below.